So the big thing that we pull out of that binary, that spectroscopic binary analysis, and the reason that I even bothered telling you guys about it is because it's primarily the way that we know how heavy stuff is in space. And that's going to come into play when we start talking about exotic stars and so forth, because they all assume that we know the mass. And so remember, when you hear that word mass, it doesn't necessarily mean like how chunky something is. It just means how much gravity it has. The word mass was essentially codified by Newton to be equivalent to gravity. So when you think about why is this, like why does a chunk of iron, why is it heavier than a chunk of hydrogen? It's like, that's a reasonable question. First of all, there's no straightforward answer for it, but generally speaking, the more atoms there are, so the more heavy something's going to be. But you also have heavy atoms, so they're bigger. They have more connectivity, more pull with respect to other atoms. We can really get into weeds with that. But the point is that from that spectroscopic binary stuff, you can get the size of those bodies, because you can untangle the way that they're orbiting each other, how fast they're orbiting each other, and how much distance they're covering. Yeah?
Did we also look at like the makeup of the star to help figure out the size?
Just the color. And so, by the way, I'll just throw this up here because it's I think there's a GIF that kind of explains this spectroscopic thing. So one of the pieces of the puzzle, and I'm going to review all these in a second after we finish, because we have a big piece of the puzzle. We have the mass. We're still working at distance, right? Because we would like to be able to say what the overall power output of a star is. And the only way we can do this is the kind of bicycle versus truck in the distance problem. It's like it's a bright light, but as I pointed out to you guys, the 20 brightest lights in the sky, for the most part, aside from the local planets and so forth, are not the closest ones. They're just really powerful, it turns out. So how do you tell the true power output of a star? That's what we're kind of working towards. We need to know how far away it is, because it could just be a bicycle that's 10 feet away, or it could be a semi-truck that's a mile away, right, with headlights. It's very difficult to discern those without knowing the distance to tell you what the true power output is. So yeah, we get the color. The color should tell us something. I have this serious reservation about the color stuff, though, because the color could be misleading. I actually have, I dropped a video, actually, in your guys' Moodle. I dropped 3 videos that my friend Pierre made. One of them is really cool, and I hope you guys will check it out. He did an experiment in his garage where he has 3 different types of material, like different metals, basically little metal blocks. And he got an IR camera so he can read the light temperature, in other words, the black body temperature off of those objects. And he basically shows that even when they're all at the same temperature, like they're essentially ambient, they've equalized with the temperature of the room, they read very different black body temperatures depending on the composition of the metal that's used. And you can see it in the IR camera that's used, right? So the color you get from the light of something in astrophysics, since we treat all of the stars as ideal gases, we assume that their emissivity is 1. In other words, all the light that they absorb, they re-emit. But that's not true for actual materials. It's only true for ideal gases. And of course, ideal gases can't give black body spectra in the first place. And so the colors could be wildly misleading us from what I could tell. In fact, even the surface of the sun, the temperature, we say, well, the surface of the sun is only 5,600 Kelvin. It's probably not only 5,600 Kelvin, because there's a lot of heat being dissipated to those convection cycles, to the differential rotation of the equator. Like there's all this motion going on. And remember, temperature just reflects motion. So all you're seeing is the temperature of the light rays themselves. You're not seeing the temperature of the material, and you can be really misled by that. So yes, we get some compositional ideas from the light, from the color, get some compositional information from the lines of the atmosphere of the star. We're going to glue that together in a moment with distance measurements and then with mass. And we're going to use all these things to try to assemble some sort of graphical representation. It's called the HR diagram, and we're going to kind of work towards that today with how we cluster all of these stars together. And what can it tell us? So Very good. What else? Any other questions about this binary, this calculating masses from the orbits of binary stars thing? By the way, what was her name? Mia, that's right. That's right. You usually have glasses on. I didn't recognize you. Yeah. Also, my eyes are not the best. Cool. What other thoughts, guys? Curiosities, questions? You want to just call on some people? You guys are making me work too hard today. Let's see. Is this person in the class? Brennick, are you in the class anymore? I don't think so. All right. How about Kaylee? Hello. Any notes from last time? Anything interesting, confusing?
I can't really remember my notes, but it was stellar
Spectroscopy. Yeah, that's kind of what we've been talking about a little bit here. What do you give me something to riff off of here? Anybody help her out? Anything interesting? Yeah. Remember your name?
Abigail.
Yes, Abigail.
Yeah, we changed it to letters to temperature and kept them.
Yeah.
And we were talking about how we have it.
Yeah, it is kind of interesting, right? I think it kind of goes back to like that really like $1 million question, which is like, hey, if gases really can't give black body spectrum, why in the heck do we think that the sun is a gas? And it's a hard question to answer, but I think you have to understand human nature a little bit to really get to the bottom of it. We still use that QWERTY keyboard, you know what I mean? There's no reason for us to use it except for we got used to it. So unfortunate, but it seems to be the case. It's also really exciting though too, because this is just how we update our gray matter. Unfortunately, things have to completely break before we come up with new models. What else, guys? Come on, I'm gonna just call on people here. Is Nate here? Hey, Nate. Anything?
I'm pretty sure not all stars have like a binary star, right?
Yeah. Well, more and more every year. Yeah.
What are like the chances that one like they have a binary star?
And you can't see it?
Yeah.
Yeah, that seems to be a huge portion of it. You know, this is actually a really interesting piece of the puzzle. Is every year, you know, I think even when I started teaching this class, it was like 80% of the stars we knew had binary partners. Now it's more than 85%. I feel like every couple of years, the better our telescopes get, the more we realize that, hey, there's actually just a really dim star there, which is the binary partner. It's hard to see stuff that's cold. There's also been a lot of, we'll get to black holes eventually, but a lot of black holes have been converted into stars recently too, because they finally realized that there was something being orbited there that was just really cold, or at least really dim. And you don't need that magical thing there to hold the place anymore. So I don't know, it seems like almost everybody has a binary partner. That's really, really perplexing because we don't have an obvious partner. And it's really, really weird. Yeah, and I think that could play into a lot of mysteries, but there's not too much to say about it. What else, guys? Anybody? Yes.
I want more on our moon.
Yeah, you should have taken last semester. The moon is pretty weird, though. You know, one of the things we'll come back to the moon later today when we build out the HR diagram. Actually, well, it's too early to say that. We'll talk about the moon in a little bit. You can actually fit, once we build this diagram and we put all the stars on a map together, turns out not only do most of the stars fit really nicely on this graph in terms of how powerful they are versus their temperature, but you can actually fit all the bodies in the solar system onto that curve, all the way down to moons. There was actually a Soviet physicist, actually a biochemist named Oparin. And I think I've mentioned before, the Soviets were very much inside of a closet of their own doing science through most of the 20th century. They weren't in communication with the West. State secrets, Cold War, all of that. But the Soviet biochemists advanced the theory that actually the origin of big rocky bodies like our Earth or even the moon is that they're kind of the leftover cores of really, really old dead stars. See, the Soviets the Soviets weren't part of this Big Bang cosmology stuff. They actually embraced a more steady state, eternal version of the universe that didn't have a birthday and a beginning, right? And when we get to start talking about the Big Bang, we're going to see that that's a pretty old idea that predates science. Like the idea that the universe was born one day is a pretty common idea in most mythological traditions. And that the church was actually a huge fan of that idea when scientists first started talking about it. Actually, the guy who came up with the Big Bang theory was a priest named Lemaitre. We'll talk about him in a little bit. He actually had to tell the Pope to lay off because it was making him look bad. So the Soviets weren't into that. And long story short, the reason nobody in the West takes Oparin's idea about the cooling off of stars and becoming planets and moons is because there's not enough time in the Big Bang model for that to happen. So the Big Bang, the Big Bang theory gives us only 14 billion years for the entire universe to be made. That seems like a long time, but it's not. If you wanted to cool a star off, like if you wanted to cool a big star down to the point that it looked like a moon, it would take trillions of years. So millions of years, not just a couple of billion years, basically. So it's an interesting idea.
I started digging onto that, and it said like our moon's not from our universe.
From our solar system.
From our solar system.
Yeah, people have played with that too. Again, the trick with that is that if you were to have a planet capture a moon, it should take a really long time for it to get stable, right? And nobody has worked out how in the world that would happen. The most popular idea for where our moon came from right now is that the Earth crashed into another little planet, and the moon and the Earth resulted from that collision. There's problems with all these models, and there's pluses to them too. But there are certainly, if you look at Saturn or Jupiter, Saturn's a great example. Saturn has moons going every which direction. So it doesn't just have a couple of moons going in this nice pattern that's in the same plane as the rest of the planets. Saturn's got moons going backwards, forwards, every direction. You've got planets like Uranus that are tipped on their side. You got Venus that's rotating the wrong direction. There's all of these little clues that something interesting has happened in all of these situations that's not quite in accordance with everything sort of formed in place a few billion years ago and has been the same ever since. So it's a bit beyond the pale of what we're talking about here. But what I want you to see is that these stories of the scientific stories that we tell about things like the moon, they actually are constrained by the cosmological story that we tell, the Big Bang theory at the moment, which is the popular cosmological story. So, again, who cares about this gaseous sun thing I've been banging on again? Well, it informs our cosmology. It informs the absolute biggest story that really constrains all the little stories that we tell. So, maybe Oparin's right, maybe he's wrong, but nobody's going to listen to him as long as we believe the universe is only 14 billion years old, because there's not enough time for his story to work out. Soviets didn't care, and it made perfect sense to them at the time. This was back in the 70s. It's weird. So yeah, there's something about science where we can only handle, as a culture, one big story at a time. If you ask somebody how the moon was formed, they're going to tell you the most popular story of how the moon was formed that people think is coolest at the moment. It could be totally different 100 years from now, but that's just the way it works. All right, thoughts? That was Kevin, right? Yeah.
You said we're going to get to the big things, though.
Oh, yeah.
Are we going to touch on? I'm a fan of big balance versus big. So we're going to touch on that.
Yeah, it's kind of like what everything's working up towards. I'm glad that we're dancing around it a little bit, because it seems so esoteric that it wouldn't matter and it wouldn't impact anything here on Earth, But it turns out that it actually constrains so much of the geological stories we tell of our own planet, of the moon, of the solar system, of really who we are, how life originated on this rock. These questions, the timetables get constrained, and they really restrict our ability to theorize too. So if we have the wrong cosmological story, whether it's Big Bang, Big Bounce, or eternal steady state universe. If any one of them is wrong, then we're going to have the wrong constraints on our theories for everything else. So it is important. We'll keep coming back to it, but the end point of this class, after we understand how all the stars work, how they're related to each other, how the galaxies work, then we're going to try to put a picture together for the whole shebang, the cosmic structures, whether different aspects of the bounce and the bangs make sense or not, how they might change in the future. I will say that the Big Bang model is, it's in some serious heat right now, which is kind of exciting. So there's a number of problems with it, especially with this new telescope that's come out, right? So maybe you guys have seen some headlines if you're nerds like me and pay attention to this stuff. But the point is that when you build a big telescope, presumably you can see further stuff. And the idea is that light takes a really long time to travel to us. In fact, the telescopes can see almost to the earliest moments. Let's say they can see almost, let's say, 13.5 billion light years away at this point. Well, 13.5 billion light years means that light traveled for 13.5 billion years to get to us. And if the universe itself is supposed to only be 13.8 billion years, then you're seeing stuff with those telescopes from 300 million years after the birth of the universe. The problem is we see fully formed galaxies that look completely mature, whereas everybody expected to see a bunch of, inchoate goo, essentially, or let's say, at least baby, adolescent, toddler galaxies starting to swirl together, or something like that, stars being formed. And that's not what they've seen with this latest powerful telescope. And it's given the whole industry a huge pause for concern. So I expect to see something change with that. I expect probably what will happen next is that the birthday will just get pushed back for a few more decades. And maybe that'll happen forever. It'll just keep getting pushed back the more powerful our telescopes get. But it is interesting, and I think it will require either some mathematical repair or a new approach to interpreting the sky. So yeah, that's interesting. We'll have plenty of time for that at the end of the course, to really look at cosmologies across the board. What else, folks? Yes?
I just have a general question.
Yes?
When talking about orbits of planets, like Jupiter and Mercury obviously they move faster than other planets. So when talking about time relative.
Jupiter actually goes kind of slow, but that's because it's so far away from the sun. So it doesn't have a lot of gravity. Yeah.
Well, I'm just saying closer planets move faster.
The closer ones for sure, yeah.
If people wanted to move there, obviously we can't. If you wanted to, the time difference between Earth and whatever planet be so drastic that you couldn't go back and forth, or go back and say if the time difference be so bad that you couldn't go back and forth.
I mean, it'd take us, I think when we send a satellite to, if we send a satellite out right now to Jupiter, it takes several years to get out there, right? So that's going really fast, like hundreds of kilometers per hour, right? Really, really fast. At some appreciable fraction of the speed of light, you can get things moving. There's no resistance in space, no air to get in the way, so you can use thrusters and get pretty fast, actually. But it takes forever to get there still. The real problem is, even if you send robots out to Saturn or something, it's something like a light hour away. So if you're working your joystick trying to drive a rover around on the surface of Saturn, you're going to have an hour delay, at least, in the signal, depending on where it's at in its orbit with respect to the Earth around the sun. So there's huge problems even with doing robotics in real time at that point, because the literal light distance, how long it takes light to get there, the radio signals, slows you down. If you're asking about actual warping of time, we'll get to that. We're going to have to talk about what time is first, though. But that's a big, big topic that we'll crack open. Yeah?
I forgot you said save for class, but I do want to talk about the other things being emitted by stars, the particles I think it was only 5, 6 years ago, I found out about like neutrinos and how we have like underground,
Mm.
we call laboratory, but to try and capture them, they observe them every very once in a while.
Yeah.
They're there.
Yeah, neutrinos are weird. Neutrinos are very weird because they seem to not interact with ordinary matter very well. So they'll seem to sort of zip right past things. Yeah, jury's still out on what neutrinos actually are. I mean, just like every other particle, it's some sort of interaction that's going on. I tend to think of neutrinos as closer to a kind of light, a sort of shock to the network, let's say. But yeah, they're very, very strange. They were completely theoretical until a few years ago, like you said, when they built these huge underwater chambers. I think they're full of heavy water of some sort, so there's more neutrons that were interacting with them.
Yeah, there's some of them like just enough to observe them.
Yeah, it's weird. But the sun does give those off. That was part of the nuclear reactions when we looked at the nuclear reactions, for sure. All right, what else, folks? Any? Yes. Yes. It's a good question. I mean, so why, like, how do we get heavy elements in the small stars? So we'll talk about the production of heavy elements when we talk about supernova. And that's a good question. Like, how in the world does our star, if it can't make heavy elements, how does it get them? Well, there's two possibilities. One, the sort of easier one to swallow is that our star is built out of, it's a second or third generation star. It's built out of the remains of other stars that have exploded already. So there's stuff that gets wrapped up into our star that wasn't made in our star. It just ended up in it because it's a huge body with a lot of mass that's attracting things to it. Actually, the star, our sun, is constantly eating stuff. It eats a lot of comets. It eats a lot of asteroids. And a lot of those contain heavy elements, right? Presumably from these processes that generate heavy elements. The main one that people focus on is supernova, and we'll talk about how that happens. It's also possible that Cebulski's star is telling us that you can make heavier elements in different ways than the ones that we're familiar with. Again, I would point towards the lattice confined fusion stuff, which I did drop a paper about if you guys want to check it out in Moodle also. But yeah, it's a good question. We'll deal more with heavy elements. Yeah. Tell me your name again. Diesel, that's right.
I was wondering, like, how long normally would it take for a star to, like, burn out?
Depends how big it is. So the big ones are going to burn hotter and brighter, and they're going to go through all their stuff faster. You know, in theory, the big ones can burn out in just a few millions of years, honestly, maybe 100 million years. The really cool ones that aren't that big, they might last for billions and billions of years. So our star, somewhere in the middle. In theory, which, you know, take it with a grain of salt because I'm not 100% sure that the theory is sound, but it should, under the current models, last for several more billions of years, five or more billions of years. That seems like a long time. And it is a long time, and it's probably beyond the scope. You know, if humans are still around 5 billion years from now, like, this is actually a good point to bring up. Can anybody picture a billion of anything in their head right now? Right? Like, can you picture, how about this? Can you picture, what's the smallest number you can picture? Like, can you picture 1,000 grains of rice right now in your head? It's hard, right? It's really hard to picture these numbers, and they're astronomical. Can you picture 100 grains of rice? No? 10? You can do 10 probably, right? All right. So 10 grains of rice, multiply that by 10. So you got 10 piles of 10 grains of rice. That's 100. Now, what if you have 10 piles of those? You get 1,000, right? And you can kind of keep doing this, right? But at some point, like, a billion is 1,000 million. A million is 1,000,000. And, like, you get into these places where it's very difficult to picture these numbers. Can you imagine, like, let me ask you this. Do you guys think humans are going to be here 1,000 years from now? Are we going to be here 100 years from now? How about 10 years from now? Probably, right? How about 10 times 10 years from now? 10 more of those intervals. Probably 100 years. It's easy. It's 1,000 years. Are we going to be here? Hopefully. Will this classroom be here in 1,000 years? Probably not. Like it'll be at least knocked down and rebuilt or something. Like it's going to wear out. What about 1,000 years though? Right? You start to get into this point where you're just like, man, that is a long time, right? That's 1,000,000 years from now. Maybe humans will have found a better rock to set up shop on by that point even, right? So, sorry, remind me the question that you asked in the first place.
Oh, I just, how long would it take for a star?
Yeah, exactly. Okay, so how long is the star going to... So it doesn't even matter if the star lasts for 5 billion more, only 5 billion more years. Well, that's 5,000 million more years. It's like, should be enough time for us to figure something out. So it's nothing to worry about, I guess, is the way that I look at it. I'm like, we have a lot of problems on Earth threatening whether we're going to be here 1,000 years from now, let alone, 1,000 more years from now. We'll hopefully have sorted out many more problems before then, other than the sun burning out. So it's not a pressing issue, I guess, is the short answer to your question. All right. Yes.
Do you think that with the technology that it would take to actually terraform and inhabit Mars, that we shouldn't just be applying that technology to making Earth more inhabitable in these areas that are about to become uninhabitable? Like, we have our own little Mars cropping up in New Mexico. Why don't we just put our little terraforming efforts down there? Why are we trying to get to Mars?
Okay, so there's a couple ways to approach that. I mean, first of all, I don't think it's a zero-sum game. Like, in other words, I don't think that just because we stop, spending money on Mars, all that money would go towards, improving inner city conditions for underprivileged children. Like, it's kind of not the way the world works, right? So I think there are kind of different budgets in some sense. I think what's appealing about Mars is that, and this isn't obvious in the news and so forth, but there's a lot of steps on the way to getting to Mars. So Mars is obviously a complete barren hellscape with terrible radiation. Nobody's going to be stoked to go and live on Mars. And if they do, they're going to be living in lava tubes underground. It's going to be a miserable place, basically, right? But the steps along the way to making that even possible might be kind of cool. Like, maybe we could take all of this toxic industry that we have on Earth and do it in the vacuum of space instead. Maybe those processes will be built out in the meantime, and Earth can be restored to a more beautiful garden, as opposed to being this place that we have to dump all our garbage into and so forth. So there might be advantages along the way while we figure it out. Also, if we actually can figure out how to restore an atmosphere to Mars and make it a beautiful place, which probably starts by getting it a magnetic field again, that's a cool process. If we learn how to do it, maybe Mars can resemble something other than a desert in Arizona, right? Without an atmosphere, right? So I don't think that it's in competition necessarily with making things better for us here. And I also think that it, in and of itself, isn't the destination. It's more of a stepping stone along the way to something much better. Because look, remind me your name again? Diesel. Like Diesel was saying, the sun has an expiration date on it. It may be 5 billion years from now, but we can't stay here forever. And there's much more obvious threatening things like our own problems, but also asteroids, comets. I mean, we showed, I think one of the last classes last semester, we went through all of the asteroid strikes that happen. We get hit with Hiroshima-sized explosions of asteroids quite regularly on Earth. There's been some in our lifetime. The fortunate part is that most humans live in a tiny little piece of the world. We almost all live in cities nowadays. Obviously, we're an exception out here. But most people, the overwhelming majority of populations, live in really concentrated areas. So when an asteroid hits the sky and explodes, and it doesn't cause a lot of damage. It might knock down a forest or something. This 300 square kilometer forest got knocked down in Russia, in Siberia, back in, I don't know, it's 1910, somewhere in the early 1900s. If that would have happened over Manhattan, right? That would have been unbelievably devastating. But the Earth is so uninhabited for the most part. You know, you probably noticed this if you guys fly in airplanes. Most of the time you're flying, you look down and it's like nothing, right? It's just forest and desert and ocean. So we have other threats in the short term that we need to face. But eventually, let's say we can survive all of that. Yeah, we probably do need to find a new home for ourselves. I actually think like a huge part of the project of why people even bother with spacecraft and so forth is this unconscious or subconscious realization that like we probably should spread out a little bit. We need a backup hard drive for this planet, basically, because bad things have happened in the past. Like we don't have dinosaurs anymore, right? Like bad things happen here sometimes, and we would be wise to have, you know, like a little vacation house somewhere, you know, that we could retreat to, something like that. Yeah, Yellowstone's another one. I don't know if you guys have heard about that, but there's like a world-ending volcano bubbling beneath Yellowstone right now. Yeah.
There's not enough magma
Oh, okay.
for it to be able to explode.
Thank God for that.
Not a danger.
All right. I will. All right. Well, I hope you're right. But there's always problems, right? And so I think a huge part of the space program, like why do we put all this money in space? It's like, I think there's this subconscious realization that like it would be wise to spread out a little bit. Maybe not in the next 100 years even, but like eventually we should probably figure it out because, I don't know, we're just kind of, otherwise we're kind of putting all our eggs in one basket a little bit. I actually do think too, like just to reiterate that if we do manage to spread out, it could actually lead to the Earth being kind of relieved of the burden of everything we're trying to do here to some extent. And it could actually make Earth a pretty, you know, nice place to live still. So just because we, you know, do all our, we do a lot of really gnarly processes here on Earth that don't necessarily have to be done here. So it's worth thinking about. All right, we should probably keep rolling here. Feel free to stop me, guys, if anything doesn't make sense or you just have a thought. I loved hearing from you guys. Okay, so we left off with how we can calculate the masses of these distant stars that are binaries, which accounts for most stars in the sky. So that's nice. So we essentially examine the orbits of these stars. We can look at their speed by how these Doppler shifts happen in their spectral lines. So that's their atmospheres. And then we can reconstruct something about their mass as a result of that. So that's a really nice piece of the puzzle. The final thing we need to work to, and I hope we get to here, I will blast through this because we need to get through it so we can move on, is how we figure out how far away they are. Before we get there, though, one last thing I didn't mention was if the star is, okay, let's back that up. I don't know if I've mentioned this before, but if you go out with a telescope and you look up at a star, can you tell how big it is just by looking at it? Can you measure how wide it is? What do you think?
If you knew a lot of numbers.
I mean, but can you just take a ruler and measure how wide the star is? No, you can't actually. And you can do that with planets, actually, it turns out. So you can actually measure an angle in the sky for a planet, and you can reconstruct based on its distance how big that planet is, right? You can't do that with stars, mainly because they're basically points of light. So the more you expose it with a camera, or the longer you look at it, the brighter and wider it appears. So stars don't actually have resolvable angular diameters. One of the only ways that we can actually get the diameter of a star that's not completely theoretical is these eclipsing binary systems. So sometimes we can see one go behind the other. And actually, when it goes behind the other, its light dips a little bit, right? So the overall light from the system goes down a little because one of the little lights goes behind the other one. And we can measure, just like with that spectroscopic binary analysis, we can measure the time it takes to go across it. And by doing that, we can get a sense of how wide that star is. And this is one of the only ways that we can actually get the radius of a star. And of course, this only really works for the bigger of the two. So it's a little tricky. People also used to do the same thing with the moon. So they'd see how long it takes for a star to disappear completely behind the moon. Not a popular method these days, but it works as well. The main way that we actually resolve distances and this will play out in a second, comes down to taking that mass estimate, and then remember this basic theoretical principle that we introduced, which is like the more mass you have, the more stuff you have, the more gravity that star has, the more fusion it's going to do, because the fusion is dependent on the pressure of all that mass bearing down on it. Therefore, the more output of light it's going to give out, right? So what scientists have done is they've actually decided that the luminosity, how much power output of light, should be directly proportional to the mass of that star. So therefore, since we calculated the mass of those stars using that spectroscopic method that we've gone over so many times now, we should, in theory, be able to derive how much power that star is putting out, which means we know the absolute brightness of that star, right? So we know all of a sudden whether it's just a little bicycle light or whether it's a huge truck's headlight, because we know exactly, if we were to put those lights at the exact same distance from us, how its real true luminosity would be. Now, this is a little bit of a problematic relationship, and actually the guy who gave us this relationship has come up before. This is another one of Arthur Eddington's machinations. So Eddington is the guy who gave us the gaseous sun, the gaseous states of equation for the sun, and introduced the idea of fusion to the stars in the first place, and brought Einstein to the Western world. So complete superstar of astronomy, Arthur Eddington. He also proposed this relationship, which is that we essentially use, when you see that little dot with a circle around it, it means our sun, right? So everything's compared as like a standard candle of our sun. So the mass of our sun, the luminosity of our sun. You compare the mass of the planet that you have over there, and you can find out the last variable would be the luminosity of that star. Sorry, did I say planet? You take the mass of that binary star that you were measuring in this last method, it will give you the true output of the luminosity. Now, this is a funny equation, and I like to use this equation to illustrate something very common in science, which is that this is a really nice equation, but you notice there's another variable up in the corner, which is an exponent, and it's an alpha parameter. And alpha parameters are interesting because we see these in physical equations a lot. What is an alpha parameter? It's basically a parameter that scales, just like we were talking about the equal sign versus the proportional sign. Well, we scaled Kepler's equations using the mass of the planets, right? So there was an alpha parameter, a complete blank in the proportionality before. Newton introduced the idea that the masses of the orbiting bodies scaled the equation and gave us the equal sign. In order to have this equal sign in this equation and not just a proportionality sign, you have to introduce an alpha parameter. And the alpha parameter is essentially just added in ad hoc depending on what color the star is, what its spectroscopic lines are. In other words, what you already think the star is like. So if I think that star is a blue giant for whatever reasons, I mean, presumably because its black body temperature is blue, and some of its spectral lines lead me to believe that it's of that quality, then I have a different alpha that I stick in versus our sun or something like that, which is going to have a smaller alpha parameter. So there's this kind of wandering variable in this relationship, which is just inserted ad hoc, so that we can get this nice line between mass and luminosity. So I guess what I'm trying to tell you guys is that this is a huge leap of faith here in some sense, that just by knowing the mass of a body that we know its luminosity. And the real kicker for this is white dwarfs, which we're going to talk about imminently, and we've kind of touched on a little bit. But we'll get back to them because we'll see a really weird situation where something seems not very luminous, but it seems very heavy. And so that kind of breaks the mold for us, and we have to tell a different story with those guys. So, mass luminosity. Okay, at this point, we're kind of ready to assemble our family tree. So we've talked about surface temperature. That was the first thing we talked about, the black body curves. The curves, you know, something that's blue is hotter than something that's red, and everything in between. So we have that. There might be some little nuanced problems with that, but more or less, that's one piece of the puzzle. We have the chemical composition from those lines in the atmosphere. we have the luminosity that we get from the masses, which we get from the spectroscopic binary analysis. We have some information about the velocity that goes into that calculation. Some rotation we touched on. Mass, obviously. Diameter is sketchy. We don't have that for a lot of stars. Okay, so what happens when we take the temperature of all these stars and we plot them against the luminosity? Does anybody, can anybody imagine, just based on, what I just told you with this diagram, what should we expect for temperature versus luminosity? How bright should something be versus how hot it is? Yeah.
The hotter it is, the better.
Yeah, right? That's logical, according to everything that we've kind of simplified to this point. The more stuff there is, the hotter it can burn. There's more pressure for fusion, right? And so that is essentially the relationship that falls out initially. So if we plot basically all the stars we see in the sky, actually this is kind of a better version of it. It's easier to see anyways. Most of the stars fall on this one line, right? So for the most part, the stars that are blue, really hot, they tend to be the ones that are most luminous according to all of these pieces of the puzzle that we pulled out so far. Some of them directly observed, some of them depend on this mass-luminosity hopefulness. But even with the mass-luminosity hopefulness, there are some stars that don't fit on that nice line down the diagonal of this graph, right? So the question that we have before us is, how do we fit all of these little hot and dim objects and all of these cold and bright objects into our story of the stars? The rest of them kind of makes sense according to the basic relationship of more stuff crushes down, makes more light. That's all pretty easy to understand with that story. Things get kind of interesting when we start trying to explain these pockets. So the ones that are really dim but really hot, we call them white dwarfs. The ones that are really bright but really cool, we call them red giants, actually. And we're going to have to start building them into a story of the lives and deaths of stars. So the story that's been constructed over the past 75 years, is one where these pockets, the white dwarfs and the red giants, are more like moments in the lives of a star. So stars will spend most of their lives at some given point on what we call the main sequence, that diagonal line. Most stars live there. And then as they die, or they age, they're going to spend some time as red dwarfs and spend ultimately some time as white dwarfs. And it's a compelling story. Some parts of it are more compelling than others, and we're going to start to pick them apart as we move forward. So, the first player in that, I think, is the white dwarf, which we've touched on a little bit. So who are we looking at here? I believe this is Sirius A and Sirius B in this drawing here. The main sequence star, so the one that's just in its normal part of its life on this diagram here, is the really bright one in the center, this blue one. There's a little tiny speck down here. Now, what's really, really bizarre is that if you do that spectroscopic analysis of the masses of these, what you find is actually that this little tiny thing is enormous compared to the really bright one. This is where things start to get really, really interesting and bizarre. So Eddington and his colleagues back in the 1920s were trying to make sense of what in the heck this could mean. What in the world is going on? This really heavy thing is giving off almost no light, and the thing that has less mass is giving off all of the light. That doesn't fit into the story of the nuclear furnace that we've built up to this point. So what do they come up with? Anybody? It's a white dwarf. What does it mean?
Dim but hot.
And how in the world would that happen? Yep. How in the world would that happen? I mean, Okay, this is the relationship between temperature. This is called the Stefan-Boltzmann law. You don't need to know that, but the point is that if you're trying to relate the luminosity, so the brightness of something, to the temperature with any body on Earth, this is actually the equation that you can use. Now, what's interesting is that Eddington and his colleagues at the time, they looked at this relationship and they said, well, if the luminosity is going down and the temperature is really big, how do I get that luminosity down? I just make the radius really, really small, actually, right? So if I make the radius really, really small, then all of a sudden I can balance this equation out. That's an interesting idea. So how do you do that? Well, what it takes is you actually have to invent a new form of matter that is incredibly, incredibly dense, right? Like as dense as thousands of metal atoms crammed into a tiny little space of a normal atom. Enormous, enormous densities that are completely inconceivable. So you're essentially saying that something as massive as our star, with all the gravity of our sun, is crammed into an object the size of the Earth. So you guys remember back at the beginning of the course when you saw these pictures of how big the Earth was compared to the sun. Remember, the Earth is already 5 times more dense than the sun. But if you crammed the whole sun into the Earth, then you could satisfy this equation such that the temperature and the luminosity made sense. So that's the solution that people have taken, and the conclusion is that there's this really exotic form of matter where essentially the atoms have collapsed in on themselves and they're behaving in this really bizarre, almost supernatural fashion. What's really interesting, though, is that we didn't talk about that little E thing at all, right? So does anybody have any idea what that E thing means? So E is emissivity. I know, you're going to have to bear with me for a second here. So at the beginning of the class today, I was like, it's really interesting if you watch this experiment that I put on Moodle, where the different metals, all at the same temperature, have different blackbody light coming off of them. What's the difference between those metals? The difference is their emissivity. They don't all absorb light equally, which means they don't give off light equally. Anything that absorbs light gives off light. Same color it absorbs, it'll give off the same color. So the emissivity of different lattices is actually very different depending on the lattice arrangement. Remember, diamond has almost no emissivity compared to graphene, soot, which has almost perfect emissivity. So all the light that you shine onto black soot is going to be absorbed and it's going to heat up in proportion and give off the same rays. Diamonds won't do that at all. They're both made out of carbon, pure carbon, but they have very different arrangements of their crystal structures and therefore they have different emissivities. So in Eddington's gaseous sun, the emissivity is always equal to 1. Therefore, it just falls out of the equation. You don't have to pay attention to it because gases always have emissivities of 1. If the stars have some sort of actual material structure to them, then the emissivity becomes really, really important. And in other words, what we could be looking at here is not an ultra-dense, compact object, but an object that's much bigger than the one that's shining bright, but it just doesn't have as much emissions because its lattice structure is incompatible with that. So those are kind of the two possibilities when it comes to thinking about white dwarfs. Either we have a new form of exotic, ultra-dense matter where we cram the whole sun into something the size of the Earth. Again, that's only possible with an ideal gas. You can't cram the Earth down into something the size of a penny. You just can't do it. You can't compress something like that to that extent. But you can do it with an ideal gas, at least in the equations it works. So those are the two stories with the white dwarf that we have to become acquainted with. When we talk about how in the heck do we end up with a white dwarf in the first place, well, either story invariably involves the death of a main sequence star, a regular star. And we'll have plenty of time to talk about the death of those two stars. Is this making any sense to anybody? Can I get like is anybody completely confused about what I'm talking about? It's okay. I will really appreciate it if you ask a question.
It feels like the two math equations are choose your own adventure.
They are.
Logic-based math, which is then just you're deciding, you know the answer you want, so you put the inputs in to get to the answer.
That's right. Yes. That's well put. And ultimately, this is what I was talking about with Michael before class. Math, look, this is really heartbreaking, but it is absolutely true. Math equations never explain anything. They can only describe the variables' relationships to one another. The really ignored part of doing science is that once you create this relationship, you do a bunch of experiments. You do a bunch of experiments and you find that this relationship holds, right? You heat a bunch of black bodies and you look at their power output, their luminosity. You come up with this equation and you're like, wow, this is great. This simple equation describes how these systems work. It does do that. The next question is why? What is going on? What causes it? Why is it that when you have a greater temperature, or why is it that when you have more radius surface area, why does that cause the luminosity to go up? Why does the emissivity matter? Does emissivity even matter in the system we're talking about? And in the case of a gaseous body, it doesn't matter because it comes a 1, which means that it just cancels out. In any ordinary substance that gives a black body curve in real life, solids, liquids, you always have to look at the emissivity because that tells you how much light that material is capable of actually giving off to you. So that's not part of the discussion, which is funny because the math equation is absolutely true, but it can obscure, if you don't interpret it properly, you can end up completely down a rabbit hole where you've invented new forms of matter that you actually have no reason to believe could even exist in the first place. But the only thing you can think of is, well, I'll shrink that radius down. That'll explain it. It works with a gaseous sun, but that would never hold with a liquid sun at all. You can't just shrink the radius down. You don't even need to, actually, because your emissivity can be affected by the mere structure of the surface. And those are, of course, very different stories that you end up telling about what happens to that star when it's dying. Does it change and crystallize its fluid structure in a new way as it ages and as its processes kind of run their course? Or does it just collapse under its own weight and eventually form these new exotic forms of matter and then keeps collapsing like an ideal gas until it, rips open physics itself and forms a black hole? It's like, well, one's a much more exciting story than the other, that's for sure. Certainly more amenable to fantastic Matt Damon films and stuff, right? But is that what we're trying to do here? I don't know. It's like, which one's more saleable? Which one's more promising in terms of the technology that comes out of it? We'll see. Yeah. Any other thoughts on this? Yes, Michael.
I'm just curious if maybe being that massive, like the gravity of those stars like white dwarfs is like restricting the ability of the electrons to like move in shells so they can't emit any light. So I guess that would also like play into like a lattice structure with it's.
Well, they do emit a lot of light. They're really bright. Sorry, you're right. They're really hot. They're not really bright. You're right. Yeah.
But I mean, something there restricting them from like going to a lower energy shell and like emitting that light. So,
I mean, absolutely. And so if your conclusion is that the radius is shrunk on these things, then you have to propose mechanisms like that.
I'm just saying like they have enough mass that they have enough gravity that it's restricting the movement of those electrons.
Yeah, I think that's the standard. I think that is the standard explanation for how in the world this all plays out at the end of the day. I think that is very much the case. But of course, that hinges on the fact that you've already sort of swallowed the Kool-Aid that the radius is as small as this equation would tell you that it is, ignoring emissivity. Which is fine. It might be the case. It may actually be the case. They may actually be ultra-dense compact objects, and their emissivities may be equivalent, and that is not the problem. I truly don't know. I just know that there is a sort of elephant in the room, which is that it's very hard to swallow that these things are made out of gaseous plasma. And if they aren't, then we actually have to deal with that term, which might explain it much better than new forms of exotic matter that we can't actually create in a laboratory or anything like that.
Yeah, that's what I mean. I think the matter itself gets weird at that point.
That's the standard explanation, my friend. Yes. And it's up to you at the end of the day. Whatever that's the cool thing. And I think it's the terrifying thing too, like you brought up, is like, look, the equation doesn't tell us the answer. equations, math, never ever explains anything. It only describes the relationship between variables. It's up to our minds to actually interpret what it means. And so, ideally, a really, really healthy scientific community would be arguing constantly about this. You would have people being like, well, I think there's problems with interpreting it that way, and the other people would be like, well, there's problems with interpreting it that way, and you would have like a very rich discourse, and much of the 19th century was like that. That's why I kind of bored you guys to death with the discussion about the material basis of the sun in the 19th century, because that's how it was originally. There was a lot of crazy ideas flying around, and people weren't so touchy about them. Like, people weren't, there was not the same sort of, everybody needs to be on the same page with respect to how we interpret a given equation like it is today. It's just a very different climate intellectually than today. So today we tend to go with one explanation until it completely breaks, and then we are in a sort of crisis mode. This is kind of what's happening with the Big Bang, and then we have to come up with a brand new idea all of a sudden, even though it might have been hanging out in the wings and the fringes for many, many years. So that's white dwarfs. What else do we have here? So we also have this other pocket up here, the supergiants and the red giants. And we're gonna get way deeper into the lives and deaths of these things soon. I'm just kind of trying to sketch out the families for you here. The red dwarfs, like, just to kind of preview that story, the idea, and I think there's some merit to this, is what's kind of interesting is you can see about midway down the main sequence, you can see that there's like, or even up at the top, you can see there's a nice transition where there's stars kind of leaking off the main sequence towards the supergiant, toward the red giant phase. Both up at the top and like kind of in the middle. There's nice little lines of stars where there's basically intermediaries, right? So the story that's told, and I think this story works for me regardless of the material basis of the sun, is that as the stars age, they become unstable to some extent. And what we're going to see is they kind of start pulsating in very interesting ways and so forth, but they expand, actually. And this works with a gas or a liquid sun. It doesn't really matter. And as they expand, they start to actually move off the main sequence. So the story that we're going to tell about these guys up in the upper left is that these are stars that are starting to die, actually. And as they die, they expand. Maybe they give off outer layers of themselves. Maybe they start doing new kinds of fusion all of a sudden because they've exhausted all their hydrogen in the core. And then something terrible happens, and they end up as white dwarfs. The white dwarf story is a little harder to tell because you don't have this nice continuum. You don't have stars that are, sort of white dwarfs, right? Like, we see stars that are drifting off the main sequence towards the red dwarf area, but we don't have stars drifting off towards the white dwarf. So that seems to be the result of something else, something more fast and cataclysmic, right? There's no obvious answer for how you get a white dwarf. Red dwarfs seem to be some evolution of the main sequence stars, so that's a little bit easier to understand. Kevin asked about the moon. What's really funny, and this is my friend Jeff actually made this diagram, but if you extend the HR diagram off the map and you just plot the temperature versus luminosity of other objects, because, hey, even the moon gives off a little bit of light, actually. You probably don't realize that, but it's probably infrared light. It's not visible light. I mean, it reflects light, so we see the moon, obviously, but it gives off a little bit. Most bodies, actually all bodies that aren't at absolute zero, so frozen completely to the point where their atoms aren't moving anymore, everybody gives off light. And you can actually plot all the bodies down the main sequence completely off the map to the point that all the way down here in the really cold region with almost no luminosity, you get bodies like Pluto and the moon, right? So everybody kind of fits on that main sequence, which is really interesting. So one thing that's really interesting too, so let me just kind of like preview this whole story. So the textbook story with this is that stars are born onto that main sequence. They have a certain amount of hydrogen, helium, they fuse, they live their lives on that main diagonal slope, right? They have a given mass, a given temperature, they live it out. As they die, they kind of drift off the main sequence, their shells expand, eventually they explode in something called a nova or even a supernova, and we'll talk about the difference later. What's left behind often is is this little core of ultra-dense material, which is called the white dwarf. That's the standard story. There's some interesting reasons to have reservations about this story, though, as well, because I think I mentioned at the end of last time, we don't see a lot of stars going bang, actually. I think I mentioned the last one we saw in our galaxy was during Galileo's time, the last supernova that we saw. That's pretty weird. Now, what we have seen, though, and this is really, really interesting, was documented by this lady. I believe she's a Spanish astronomer. And we did a really interesting podcast with this lady, but she basically did this study where she got a hold of these military photographs of the night sky that spanned like 50 years of time. So presumably the military was, I don't know, trying to watch out for Russian satellites or something like that. But they were taking pictures of the same region of sky over 50 years. She got a hold of these photo plates, and she started looking across time, and she noticed that a lot of apparent, what you would say are stars, little orbs glowing in the sky, disappeared over the years. A number of them, quite a few actually, which is really interesting. And she tried really hard in the paper. I'll link this paper in Moodle too if you want to check it out. It's very unfun to read, but you can see the data for yourselves. She tries really hard to come up with answers for, and she talks herself out of a number of them. She's like, well, that could be like a scratch on the photographic plate, or there's this other astrophysical process, like one of them, she comes up with every possible explanation she can other than the fact that the stars just went dark. But she's still left at the end of the day with hundreds of these stars that seem to have literally just gone out over 50 years, which is really, really weird. And in all honesty, it kind of opens up the door to the idea that instead of this standard story where we have these stars moving off the main sequence and exploding and dying, there might be something more mundane going on where these stars just kind of cool off over time, right? And at some point, like we talked about with the brown dwarfs and the stars, one atom less and you're a brown dwarf all of a sudden. You don't have the mass to do fusion anymore. And so what? You look like a Jupiter that's kind of heavy all of a sudden. So there's a really interesting story that's a little bit more mundane. Now, why isn't that story told in the textbook? And this is full circle. It's the last thing I'm going to tell you guys today. Why don't we tell that story? It's kind of related to the Aparan Soviet story that I told you guys.
Because the universe would have to be older.
That's right. That's right, Summer. That's exactly right. It would take a very, very long time to cool stars off the main sequence. It would probably take on the order of trillions of years. If our universe is really only 14 billion years old, there hasn't been enough time for such a thing to happen. So let's put a pin in it there, and we'll look at each one of these processes in more detail next time. But yeah, have a great weekend, guys. Yep.